Okay, exercise 17 next. Here we are given an abelian group which has more than 3 elements of order 2. That means there are at least 4 elements of order 2 in an abelian group. Then we have to show that the group actually has at least 7 elements of order 2. And the second part of this exercise asks us to find an example that shows that this is not necessarily true if the group is non-abelian. So let's see the solution. So let's start by considering such a group. Let G be an abelian group having at least 4 elements of order 2. Choose okay, so now we are going to choose 2 such elements that are distinct, that is they are different from each other and they are of order 2. Okay, we can do this because we anyway have at least 4 such elements. We can choose 2 more, which we will do, but in a slightly in a clever manner, so that we can make use of this whole hypothesis. Then AB is not equal to the identity element, because otherwise if AB equals the identity element, we have this. Oh, so what am I writing? Not AB whole square. Then A can be written as AE. In place of E we can write AB, and this gives us A square B. But since A has order 2, so A square is identity, and this is equal to B, contradicting the choice that A and B are distinct. Okay, so AB is not equal to identity, but now we are going to show that AB whole square equals the identity. Since G is abelian, AB whole square can be written as A square B square, but A and B both have order 2, so both of these powers equal identity, equal to this. Thus the element AB has order 2 because its first power is not equal to the identity, but its second power equals the identity. So we note that we have got already got one new element of order 2, AB. Why am I saying that AB is a new element? Because of the cancellation laws, AB cannot be equal to A, because if that is the case, then you can cancel A from both sides and conclude that B is equal to the identity, which is not true. Why is that not true? Because if B is the identity, then the order of B is 1, contradicting this. Similarly, AB cannot be equal to B either. So we have got three distinct elements of order 2, A, B and AB. Note that AB does not belong to this set, so that A, B and AB are three distinct elements of order 2 in G. We still can choose one more, and we are now going to choose that. Since G has at least 4 elements of order 2, we choose an element C belonging to G such that C is of order 2 and C is different from these other three elements of order 2. Okay, so this choice we can make. Now consider the elements AC, BC and ABC. Okay. We have AC not equal to identity, much like how AB is not equal to the identity. Since otherwise and this contradicts this relation. Similarly, BC is also not equal to the identity and ABC is not equal to the identity. In showing that BC is not equal to the identity, just like this, you will of course use the fact that B has order 2. What about ABC? In this case, you use the thing that we have proved, that AB also is an element of order 2. So this also cannot be equal to the identity. Furthermore, AC whole square, because the group is Abelian, now we are doing a calculation like this one. So A square C square this is equal to EE, owing to the fact that both A and C are of order 2. This is equal to E. And similarly, BC whole square is equal to E, and ABC whole square is also equal to E. So these elements AC, BC and ABC, they are also elements of order 2. Now the question is, are they something new? Are they new elements in the sense that are they different from these elements of order 2 that we already had before having these 3 elements? And that is the case. We are now going to show that. But before that, let's just notice one more thing, that these elements are 3 distinct elements. None of them is equal to the other. It's easy to see that AC, BC and ABC are all distinct. Why? Let's just see. If AC is equal to BC, if you suppose that, then you can cancel C from both sides. That will give you A equal to B. But A and B, originally we chose them to be distinct elements, so that is contradicted. So AC and BC cannot be equal. If AC and ABC are equal, then because of the fact that the group is abelian, you can cancel A and C from both sides, giving you B equal to the identity. But we have already seen that since B has order 2, it cannot be equal to the identity element. So AC and ABC cannot be equal. Similarly, BC and ABC cannot be equal, because if they are, then A is the identity element, which again is not possible. So they are indeed all distinct. Now our next claim is that none of these 3 elements belongs to the set consisting of A, B, C and AB. None of them belongs to this set. The cancellation laws in G imply that, say, let us first see how AC is not an element in this set. The cancellation laws immediately imply that AC is neither equal to A nor equal to C nor equal to AB. If AC is equal to A, then C is identity, contradicting the fact that C has order 2. Similarly, if AC is equal to C, then A is identity, that is also not possible. And if AC is equal to AB, then B is equal to C, and that contradicts the fact that B and C are actually not the same thing. That AC is not in this subset A, C and AB. if AC, so that leaves us with only one case. What happens if AC is equal to B? Then C is equal to, C can be written like this, let's write EC. Okay, in place of E we can write A square C AAC, but AC is equal to B, so AB. Which is a contradiction. What does it contradict? It contradicts this. C cannot be equal to AB. So AC does not belong to this. So 1/3 of this last claim has been proved. The other 2/3 I leave it to you. Similarly, neither BC nor ABC belongs to this set. Prove it. Hence, G has the following 7 distinct elements of order 2. It may have more, but at least 7. A, B, C, AB, and then the 3 more elements, AC, BC, ABC, and they are all distinct. We have already proved that. So this completes the first solution. Then the second one, 18. Suppose that A is a group element A is a group element and A to the power 6, the 6th power of A equals the identity element. What are the possibilities for the order of A? Give reasons for your answer. Okay, so we will look at the situations one by one. If A happens to be equal to the identity element, then order of A is equal to 1. Okay, because that is the only element in any group that has order 1. So now assume that A is not equal to the identity element. Under this assumption, if we now assume that A square is equal to the identity, then 2 is the smallest positive integer for which this equation is true. So in this case, the order of A will be equal to 2. Then order of A is equal to 2. So this also we assume to not be the case. Assume that A square is not equal to identity. So note that we now have made two assumptions. Neither A nor A square equals the identity element. So both of these things are now with us. Under them, if A cube equals the identity element, then the order of A, by definition of order of an element in a group, is equal to 3. So we assume that that is also not the case. So far things are going extremely in an extremely straightforward manner. Okay, but now things will change. So we have now assumed that neither A nor A square nor A cube is equal to the identity element. But what about A to the power 4? Can it be equal to the identity element? We will show that it cannot be. Suppose A to the power 4 equals E. Then A square, which can be written as A to the power 6 minus 4, is equal to, you can use the rules of exponent to write the product, that power like this, product. Okay, A to the power 6 times the inverse of A to the power 4. Now it's given in the hypothesis that this power is equal to the identity, and we are supposing that this power is equal to the identity. So this is E inverse, that is equal to E, and that means that this shows us that A square has to be equal to E, which contradicts our assumption, which contradicts our assumption that A square is not equal to E. So that means we cannot have A to the power 4 equal to E. So is wrong. Next, suppose A to the power 5 is equal to E. Then A, which can be written as A to the power 1, becomes this. This is identity from our hypothesis, and this is identity from our supposition. which contradicts the assumption that A is not equal to E. Hence, the supposition that a to the power 5 is equal to E is also wrong. That means now neither a nor a square nor a cube nor a to the power 4 nor a to the power 5 equals the identity. Only a to the power 6 is equal to the identity. So taking everything into consideration, we can now conclude that the order of A is 6. Hence, the equation this implies that order of A is equal to 6, and this completes the solution. So there are exactly 4 possibilities for the order of A. It's either 1 or 2 or 3 or 6. Okay, so that is exercise 18. Then 19. If A is a group element, and a to the power 6, oh sorry, I was taking down the previous one again, and A has infinite order, prove that a to the power m is not equal to a to the power n when m and n are different. So in this context, m and n are different different integers, not necessarily positive. Okay, so we will have to prove this. If A has infinite order, then distinct integers produce distinct powers of A in G. Contrary to this claim, we will suppose that there exist 2 distinct integers for which the same power is produced, and then we will try to arrive at a contradiction. Suppose there exist integers m and n that are distinct such that these 2 powers are equal. Now because m and n are distinct, so one of them will definitely be greater than the other, and without loss of generality we can assume that m is greater than n. m is greater than n. Now let's look at the power a to the power m minus n. Using the rules of exponent available in the group, we can write it like this. Now we use this equation. And so this becomes the identity. Now note that because m and n are distinct integers, no doubt, but they are any integers, so each one of them can either be positive or 0 or negative. We don't really know. But the important thing here is that no matter what the signs of m and n are, since m is greater than n, m minus n is a positive integer. Since m minus n is a positive integer, the above equation implies that this is finite. Order of A is finite. Because we have got a positive integer for which the corresponding power equals the identity element. And in fact, the largest possible value of the order is m minus n itself. And this is a contradiction to the hypothesis that A is of infinite order. Which is a contradiction to the hypothesis. There is no need to write to the hypothesis that A has infinite order because that is the only hypothesis. So our supposition is wrong. That means if m and n are distinct integers, then the powers can never be equal. They will also be distinct. Okay. Then (20). Let X belong to a group if x square is not equal to the identity, but x to the power 6 is equal to the identity, prove that x to the power 4 and x to the power 5 are both different from the identity element. Also, what can you say about the order of the element x? Let me put some ink first. Okay, so we have to prove that x to the power 4 cannot be equal to the identity. So let's suppose the contrary. Then x square, here the strategy is exactly like the one we have seen in the solution to exercise 18. You are given a hypothesis and you suppose something, together they produce a contradiction. Which contradicts this hypothesis. That is, we must have this. Next, suppose we want to prove this, so we suppose that its negation is true. This implies, so here we have got the equation that x is equal to e, but then if x is equal to e, then x square is also equal to e. A contradiction again, this is contradicted. So our last supposition is wrong, and we must have x to the power 5 also not equal to e. Now we have to figure out something about the order of x. What can it possibly be? Since x is not equal to e, because if x is e, then x square is e. And x square is not equal to e either. We have the order of x not equal to 1 and not equal to 2. It can neither be 1 nor can it be 2. The case that x is an element of order 3 is a possibility. The order of x may be equal to 3. If order of x is not equal to 3, then combining this with these inequalities, that neither x to the power 4 is equal to e nor x to the power 5 is equal to e, which imply that the order of x is neither equal to 3, neither equal to 4 nor equal to 5, we conclude that the order has to be equal to 6, because note that the equation x to the power 6 equal to e is already available with us. So if the order is not 3, then it has to be equal to 6. So these are the only two possibilities for the order of the element x. Then show that if A is an element of a group G, then the order of A is always less than or equal to the order of G. Okay, now nothing has been said about the element A or G, in terms of their order. That is, it has not been said that they should be of finite order. They may be of infinite order also. So before even showing that this inequality is true, we have to interpret this inequality properly. What is the meaning of this inequality when, say, one of these or both of them are infinite? If order of A is infinite, say this is infinite, then the inequality looks like this. Okay, and this inequality in general is, although it looks like something wrong, it is wrong, or rather not wrong, it is meaningless in the system of real numbers. However, in the system of extended real numbers, which consists of the set of real numbers along with the two additional objects, minus infinity and plus infinity. There, in this larger system, this inequality makes sense only when this is also equal to infinity, where by infinity we mean plus infinity. Okay, the usual ordered relation that we have in R can be extended to this extended real number system by defining this. Say A and B are two extended real numbers. That means each one of them can either be a real number or plus infinity or minus infinity. If both of them are real numbers, then this inequality has the usual meaning that it has in this smaller system R. If this is equal to plus infinity, then the inequality is true for any extended real number A. If A is equal to minus infinity, then also this inequality is true for any extended real number B. If B is equal to minus infinity, then this inequality is true only when A is also equal to minus infinity. And when a is equal to plus infinity, then this inequality is true only when b is also equal to plus infinity. In short, the order relation that we have in R, this is R, no, this real line without any bounds, it has been extended to this larger set by defining minus infinity to be smaller than every real number, strictly smaller than every real number and plus infinity, and by defining plus infinity to be strictly larger than every real number and minus infinity. In this extended system, this inequality makes sense. Okay. So now, so that means cases will come. Assume first that A has infinite order. Okay, so if A has infinite order, then by the result of exercise 19, distinct integral powers, integral powers of A given by distinct integers will all be distinct. Then by exercise 19, the elements E, A square, A cube, etc. in G are all distinct. Of course, these elements are all in G because of closure property. Hence, G is infinite in this case. And we have equality in this case, which is also included in this inequality because we have the provision for equality. Okay. Next, assume A has finite order n, say, where n is some positive integer, which is the order of A. If G is an infinite group, I don't know whether I should write like this. Instead, let's just write it in words. If G is an infinite group, then there is nothing to prove, because in this case the inequality looks like this: n is less than or equal to plus infinity, which is true. So assume that G is finite. Okay. Now we claim that the elements E a square all the way up to a to the power n minus 1 in G are all distinct. Suppose contrary to this claim we have collapse. Collapse means we have repetition. Suppose there exist integers I and j such that this and a to the power I is equal to a to the power j. This supposition simply means that two distinct elements from this list of elements are equal. Distinct in the sense that they look distinct, the symbols look distinct. One of them is a to the power I and the other is a to the power j. Since I and j are not equal, so without loss of generality we have assumed j to be greater than I, and since I and j both have to lie between 0 and n minus 1, so we have these inequalities. But then a to the power j minus I is equal to the identity element, and j minus I first of all is a positive integer because of this inner inequality. Then j minus I is less than or equal to j. Why? Because I is a non-negative integer which we are subtracting from j. So j minus I either is equal to j precisely when I is 0, or if I is positive it is strictly less than j. J itself is less than or equal to n minus 1 and n minus 1 is strictly less than n. This contradicts the fact that the order of A is n, because if the order is n, then n should be the smallest positive integer for which a to the power n is equal to e. But here we have a positive integer j minus I smaller than n for which such an equation is true. So this is a contradiction. So our last supposition is wrong, and hence the elements in G are all distinct. So that means G has this many elements at least. It may have more, may not have more, we don't know. Now how many elements are there in this list? N elements. Starting from A all the way up to a to the power n minus 1, there are n minus 1 elements. If you include E also, then you get n elements. Hence, the order of A, which is equal to n, must be less than or equal to the order of G, because G has at least n elements, it may have more. So this completes this solution. Next, show that the group U14 of integers less than 14 and positive integers less than 14 and relatively prime to 14 under multiplication modulo 14, it's that group. It is generated by the element 3 and also it is generated by the element 5. So this means U14 is cyclic. Also, is U14 generated by the element 11? Let's first list the elements of U14. Here we have the positive integers less than 14 and relatively prime to 14. If you want to know beforehand how many elements U14 has, then you have to calculate the Euler phi function value of 14. There is a formula, as you may know. The prime factors of 14, the distinct prime factors are 2 and 7. So the formula is this, and it gives us, if you calculate, this will be 1 by 2, this will be 6 by 7. So the denominator cancels this 14 out. Here we have 1 and here we will have 6. So there will be 6 elements in U14. And the elements are these. So because of 2 and 7, we cannot consider even numbers. 1, 3, 5, 7 of course also has to be avoided. Then 9, 11, 13. Now, to show that 3 is a generator of this group, we have to look at the integral powers of 3 and show that all the elements are appearing in those integral powers. So 3 to the power 1 of course is 3, and 3 square is 9, and 3 cube is 27, but modulo 14, 27 is equal to 13. Then 3 to the power 4, I have the calculations done here. Three to the power 5 is 5. 3 to the power 6 is 1. So U14 is actually generated by 3. Just like that, let's calculate the integral powers of 5 also. Five square is 11. 5 square is actually 25, but modulo 14 it's 11. 5 cube is 13. 5 to the power 4 is 9. 5 to the power 5 is 3, and 5 to the power 6 is 1. So you can see that here also all the elements are appearing 1, 3, 9, 5, 11, 13. That is 1, 3, 5, 9, 11, 13. Hence, U14 is also generated by 5. Note that, however, if we try to look at the calculation for 11, we will see that we won't get all the elements of U14. So 11 will not be a generator of U14. Eleven square is 121 modulo 14, that is 9, and 11 cube is 1. Now after this, if you continue, 11 to the power 4 will be equal to 11, 11 to the power 5 will be equal to 11 times 9. The thing is that you will be trapped among these three values only. So U14 is not equal to the cyclic group generated by 11. Note one thing, however, that although U14 is not equal to this cyclic group, this is nonetheless a subgroup of U14, and it consists of these three things: 1, 9 and 11. Okay, so it's a subgroup, but it's not equal to U14. Next, exercise 23. Show that U20 is not equal to the cyclic group generated by K for any K in U20. So unlike U14, U20 is not cyclic. And this I leave to you. What you have to do, you first figure out the elements of U20. You have the set ready in front of you, and then you start calculating the powers of all the elements. You take the elements of U20 one by one. You calculate the integral powers. You will see that in each such case, the situation is something like this. The element will not be, no element will be capable of generating the entire U20. And in that calculation, clearly, just like what we have here, you have to avoid the identity element 1, because all the integral powers of 1 are going to be equal to 1. So that is known. Now for the other elements, all the non-identity elements have to be checked individually. So you please do this one and convince yourself that U20 has no generator and hence is not a cyclic group. Next, (24). Suppose n is an even positive integer. and H is a subgroup of Zn or Cn. Prove that either every member of H is even or exactly half of the members of H are even. Zn is the group of integers modulo n, and the binary operation is addition modulo n. In this text, however, the author is not considering the elements of Zn as congruence classes. He is considering the elements of Zn as ordinary integers. However, nothing essentially changes because the groups are isomorphic. In whatever manner you interpret the objects or the elements in it, after all, the group structure is the same. Okay, so let's see the solution. So it has been said here that n is even and H is a subgroup of this Zn or Zn. Now we have to prove that either every member of H is even, or if there is at least one odd member in H, then exactly half of the elements of H are even and half are odd. And in particular, this means that in this case the subgroup H itself has an even number of elements, so that it can be divided into two equal halves. If every member of H is even, then we are done. Then we don't have to show anything. Okay. So assume that H has at least one odd member. Okay, now since we are dealing with a finite set H, so there will be a smallest member, because after all the members are positive integers, in fact non-negative integers. So let and one more thing is that this assumption means that H is not the trivial group consisting of only 0, because then there is no odd member in H. Let K be the smallest non-zero element in H. K is positive actually, but we are assuming non-zero. then that means k is positive because we don't have any negatives here in Zn. We now claim it will be nice to mention this. Note that k is positive. We now claim that the subgroup H is actually equal to the cyclic subgroup generated by K. That is our claim. We are now going to prove this claim. Let H be any element in H, then H is a non-negative integer and K is a positive integer. We can now divide H by K to obtain a unique quotient and a unique remainder. Now, there exist unique integers Q and R such that H is equal to Qk plus R, where the remainder R is non-negative and is less than K. Then R is equal to H minus Qk, and this belongs to the subgroup H. Why? Note that K being the smallest non-zero element in H is after all an element in H, and we have chosen H to be an element of H. So both H and K are elements of the subgroup. Then we are saying that this H minus Qk is also an element of the subgroup. What is this element actually? Since our group is abelian, so we are using additive notation. But in a general group where we don't know whether it is abelian or non-abelian, we use multiplicative notation. In multiplicative notation, this expression looks like this. Where H and K are elements of the subgroup and minus Q is an integer. So from this you can clearly see that this belongs to H. So we now have the fact that this R belongs to H. Now let's look at the inequalities. The nature of K is that it's the smallest non-zero element of H. Now R is smaller than K and R is an element of H. So R cannot be non-zero because then the minimal nature of K will be contradicted. Since K is the smallest positive element of H and R belongs to H, the inequalities 0 less than or equal to R less than K imply that R has to be equal to 0. It cannot be positive. If it is positive, then the minimality of K is contradicted. But then H is equal to q times k, and because h is non-negative and k is positive, q itself is it has to be a non-negative integer. So that means either q is 0 or it is positive. When q is 0, fine, h is also 0. When q is positive, h is k plus k plus k, q times. So that means h is generated by k, and this shows that any arbitrary element appears in the powers of k. In the additive notation, you have to understand that qk actually means k to the power q. Okay, so h appears as a power of k. So that's why capital H is generated by k, or it's equal to the cyclic subgroup generated by k. This shows this proves our claim. Now the question is, okay, now what? Now how are we going to use this claim to actually show the thing that we have been asked in this exercise, that in the case when h has at least one odd member, then exactly half of the members of h are even. So let's now see how that can be obtained from this information. Now since k is an element of h which is finite, so by the previous one previous exercise where we proved that if a is an element of a group G, then we have this inequality. If you apply this inequality for h, where you have h here and you have k here, then finiteness of h tells us that k has finite order. So we are just simply going to write like this: since h is finite, order of k, oh, here the notation is something else. Order of k, let us denote it by the symbol s. This is also finite. That means this is a positive integer. Now sk is equal to 0 because the order of k is s, so sk is equal to 0. But since we are in Cn, which is the additive group of integers modulo n, this means that sk is divisible by n. Which implies sk is equal to nl, that means it will be a multiple of n for some integer l. Now note that originally in the exercise it was okay. Before we show, what the hell? before we say these things, we have to observe one more thing. K is a positive, K is the smallest positive integer in H, fine, but our claim now is that K has to be odd. Why? Because since K is generating H, if K is even, then all the elements of H will be even, and we have assumed that H has at least one odd member. Since K generates H, which has at least one odd member, K cannot be even. Now we can write those other things. Since H is finite, this is also finite, that means it's a positive integer. Okay. Then let's write it at once. Sk, which if you write in multiplicative notation, it will be k to the power s. This is equal to the identity, so it will be a multiple of n. This is equal to nl for some integer L. Okay. Now it is given that n is even in the original exercise, but k is odd. So to maintain the evenness of the left hand side, s has to be even. Since n is even and k is odd, s must be even. So now let's look at the actual elements of H. Since H is being generated by K, its elements will look like this: 0, K, 2K, 3K, etc. up to S minus 1 times K. In the group Zn, Sk is equal to 0. So here the things end. And anyway, it has S number of elements because the order of K is S. So the cyclic subgroup generated by K will have exactly S elements, which is H. So H has S elements, and these are the S elements, where the even members are precisely these: 0, 2K, 4K, etc. How far can we go here? Note that since S is even, S minus 1 is odd, and here we are considering even multiples of K, so we have to go up to S minus 2K. And there are how many of I mean how many elements are there in this list, in this final list, that we will obtain if we divide this s minus 2 by 2. Why? Because you see, if you start with this one, then this is one element, then two elements, then 3 elements. Shall we get it like this? I mean what I am trying to say is this. If we start from here, instead of considering 0 first, let's start from this element. This is one element. Including this one, we have 2 elements. So that 1 and 2, that is obtained by dividing the number, the coefficient, by 2. So if we calculate all these elements, then in total there will be s minus 2 divided by 2 elements. Does it make sense? Yes, it makes sense, because s minus 2 is even. So this is an integer, it's a positive integer. So s minus 2 divided by 2 plus 1 additional element. So this many elements are there in this list, and there are s minus 2 divided by 2 plus 1, which is equal to s minus 2 of them. So in the original subgroup, the number of elements is s, and the number of even members is precisely half of them, s by 2. So this completes the solution. After this, the exercises continue with some problems on dihedral group, and then many other such things. Let's just end the exercises here, so we will continue in the next video. And if you have any doubt regarding these problems, and if you spot any mistake, please let me know in the comment section below, like some of you are doing, but not many are actually, especially here, not many are really bothering. That is a little bit unfortunate. So please let me know if there is any mistake. We will try to rectify the things together. So with that, I end this video here. That's all. Signing off from a mathematical room. Have a nice night.